Okay, so for this example, let the function be defined by e to the 2x for x values between 0 and infinity. R is going to be the unbounded region in the first quadrant below the graph of the function. And notice the question, find the volume of the solid generated when R is revolved about the x-axis. Okay, so let's get a little picture of that. E to the negative 2x is going to come down something like this. Okay, so we want to consider the unbounded region in the first quadrant from 0 to infinity, so that's going to be all this space right here. And what's interesting about this problem is that we're going to rotate it around the x-axis. So taking all of this space right here. Notice that it's unbounded. Okay, so as you rotate around the x-axis, okay, this region gets thinner and thinner and thinner, almost like a needle point. Okay, so we're going to find the volume of that solid when we revolve about the x-axis. So let's go ahead and put in our representative rectangle. Okay, and notice that the unbounded region always touches the axis of revolution. So the method of finding the volume is going to be with the disk method. And as a reminder, that formula is volume equals pi times the integral. And here we're going to go from 0 to infinity of the radius squared. Dx. Okay, so that's the formula we're going to be using. Alright, so let's go ahead and finish setting up our integral. So the volume equals pi times the integral 0 to infinity. Okay, let's get an expression for the radius. The radius of each and every one of those disks. And we're going to square it. And it's with respect to x. So when we come back here and we look at our representative rectangle, the radius of any one of them is going to be the distance from the function to the x-axis. So this is y equals 0, and this function is y equals e to the negative 2x. Okay, so at this particular x value right here, somewhere inside of this representative rectangle, okay, the distance from the curve to the x-axis is going to be the difference, the top minus the bottom, e to the negative 2x minus 0. So we're just going to consider e to the negative 2x. Okay, so we have, and this is just negative 2x. So we have our integral set up. We realize it's improper. We're going to have to rewrite it as a proper integral. Okay, so let me go ahead and do a little cleanup on this though. Pi times the integral, ugh. And I'm going to do a little algebra here and clean this up. So e to the negative 4x when we multiply the exponents dx. Okay. So let's rewrite it as a proper integral. And I'm going to leave the pi out in front of the limit statement. The limit as b goes to infinity of the integral from 0 to b of e to the negative 4x. Okay, so to evaluate this integral, we might want to use U-Substitution. U is going to be the exponent. So U is going to be negative 4x. And du would be negative 4 dx. So I'm going to have to bring in a negative 4 and pull out a negative 1/4. And when I pull out the negative 1/4, I'm actually going to put it over here by the constant pi. Okay, so wrapping around down here, I have negative 1/4 pi, or maybe negative pi over 4 in the next step, times the limit as b goes to infinity of the integral e to the u du, with limits 0 to b. Okay, integrating, I go back to e to the u being negative 4x, and in my next step I'll evaluate at the limits 0 to b. I think I left off a pi. Here's the pi. Here's the pi. So we're going to have e to the negative 4b minus e to the 0 when I plug in those limits. So a little cleanup here. I'll apply the limit. I'll multiply the answer by negative pi over 4. Now I think actually I'm going to wrap it down here. I have the room. So negative pi over 4. I'm going to stack it now. Okay, I don't like to work with negative exponents, so I'm going to rewrite it as 1 over e, 1 over e to the 4b minus e to the 0 is 1. Okay. Now I'm ready to apply the limit part of this, so I'm going to plug in infinity for b and see what happens. So negative pi over 4 times, okay, and so plugging in positive infinity, I'm going to end up with 1 over e to the 4 times infinity, which is just really large, okay, minus 1. So negative pi over 4. And I use parentheses whenever it's convenient, when I'm worried about, you know, kind of keeping things together. Okay, so sometimes I use parentheses, sometimes not, just to kind of keep it all organized. Negative pi over 4 times, okay, when we look at 1 over e to the infinity, that's going to be 0. So 0 minus 1 is negative 1. As a final product, we're going to end up with a volume of pi over 4. So we can say that this integral converges, it converges to the number pi over 4, since I didn't reach an infinity. So we're still thinking about the words convergent and divergent. Okay, as a final example in this video, we're going to look at this next one right here. It's pretty involved. We're going to evaluate this improper integral. We're going to make it proper, and then see what happens. As I begin to think about how am I going to integrate this integran, some options are, well, I guess you could distribute the e to the negative x, and if you did that, that distribution would give us e to the negative x minus the product x e to the negative x. I'm still going to have to do integration by parts, irregardless of whether I leave it as is or whether I distribute the e to the negative x. So integration by parts, because of this right here, this product, would have to take place. So the way it is right now, I think I'm just going to leave it and not distribute it and just go right to integration by parts. Okay. But if you did distribute it, of course you wouldn't have to use parts on e to the negative x. That's pretty easy. It's just that the second term would require that technique. Okay, so I guess integration by parts. So we need to figure out, okay, well, what is u going to be? And we have to go back through the Lipit idea. L being logarithmic, not present. I being inverse trig, not present as one of the factors. P for polynomial, yes. That's going to be the quantity 1 minus x. That is a polynomial. So this might be my u, and this is going to be my dv. So parts over here. Establishing what u, du, dv, and v are. This is an evil problem. It's probably one of the more difficult ones because of integration by parts involved in an improper integral. Okay, so let's go to now finding the antiderivative here. Okay, so thinking about what that looks like, I'm going to lose the integral symbol, and I'm thinking about ultraviolet voodoo. So ultraviolet, U times V. So 1 minus X times this V. So that's a negative. I think I'm going to manage the negative right here and keep the e to the negative x back here as this factor. Minus the integral of voodoo. Okay, so when I multiply these two, I'm going to get a positive e to the negative x dx. And I need to evaluate all of this from 1 to b. And those are the limits here as well. But I still need to do some work here before I can actually do the evaluation part. So I'm going to come down here. Like I said, this problem's evil. Let's kind of hang in there with it. The limit as b goes to infinity. Okay, then coming back here and looking at this part of it, I still have some more work to do. And this antiderivative, come down here and put a minus for this subtraction, that's easy to integrate, and that goes back to a negative e to the negative x. So that negative, I'm going to make this addition, and e to the negative x, evaluated from 1 to b. Alright, so now the evaluation part of this gets kind of tedious as well. Not ready for the limit yet. Okay, this entire function evaluated at b minus this entire function evaluated at 1. So I try and start by plugging in b first. Hopefully that's enough room for everything. Alright, so this would be negative 1 minus x. It's a 1 minus e to the negative b plus e to the negative b, goodness, minus, now it's time for 1 to go in everywhere, and before I put 1 in everywhere, I'm going to do a double check on this. Looks like we need b to go in here for x. I'm thinking that needs to be a b right there. Whew. That looks about right. Now minus, goodness, plug in 1 everywhere. This is minus a negative 1 minus 1 e to the negative 1 plus e to the negative 1. Goodness. Alright. Let's see if we can do some cleanup on this. Okay, looking at this term right here, I'm not sure, maybe it'll be helpful if I pull the negative b to the denominator. So I'm going to have negative quantity 1 minus b over e to the positive b plus 1, that's a plus, 1 over e to the b. Okay, and then minus, and let's come over here. 1 minus 1 is going to be 0. So 0 times anything is 0, so this entire term is going to go to 0. So it's going to be minus 1 over e to the first power. Okay, a lot of calculations here, just kind of tedious, but what I can see here is that maybe if I distributed the negative here into this quantity here, I might be able to do a little cleanup before I find the limit. So let me see what happens there and takes place. It's getting pretty involved. So we have negative 1 plus b over e to the b plus 1 over e to the b minus 1 over e. Okay, something we can do is I can take this fraction and separate it into 2 single fractions by putting e to the b under each of these terms. That would be convenient because when I put e to the b under -1, it's going to cancel with this term. So I think I'm going to go that route. And as I think more about this problem, I'm thinking maybe in the beginning I should have distributed. This is getting kind of tedious. Plus b over e to the b. All I did was separate right here. And we still have plus the remaining two terms, 1 over e to the b minus 1 over e. Okay. So now thinking about what we have, I can cancel these two terms. Yeah, I'm wondering if we should have distributed in the beginning. It might have made it a little easier. Maybe a little. So b goes to infinity. And what do we have? Finally, we have b over e to the b minus 1 over e. Okay. So now we have the limit. I'm going to do something here. I'm going to use a property of limits. I'm going to separate for a reason because I see what's going to have to happen. Now I'm going to apply the limit. And it looks like it's making it more complicated, but I think it's going to be easier to manage. Okay, I know this answer right here is just going to be 1 over e. It's over here that I was concerned about and what I saw. If I plug in infinity for b and infinity for b here, I'm going to get indeterminate infinity over infinity. So what that tells me is I need to use L'Hopital's rule. Oh my goodness. Okay, so L'Hopital's rule to find the limit. Okay, and just think of b as x. b is x here and x here. I can use L'Hopital's rule, even with b's, it doesn't matter. So the derivative of b, or x, would just be 1 over the derivative of e to the b with respect to b would just be itself. Okay, and that's going to be more manageable. Okay, and to finally fix this, clean it up, plug in infinity for b. That's 1 over super large, so that's going to go to 0. 0 minus this limit is just going to be 1 over e. So yep, that's it. That's my final answer, -1 over e. You can check it on the 89, I know for sure, by putting that into y1 and evaluating using an infinity limit, and you should get -1 over e. Wow. This would be an entire free response question because of the length of time it took and all the skills that are involved in it. Integration by parts, with limits, L'Hopital's rule, etc.